Let us look at logistic regression. Logistic regression is a kind of probabilistic classification. In probabilistic classification, we train classifiers to estimate a function, mapping an input x to an output y, or to estimate the probability of y given x. There are two categories of probabilistic classifiers. The first category is called discriminative classifiers. And here we assume that the function forms for probability of y given x. And the objective is to estimate the parameters of probability of y given x directly from the training data. Another category is called generative classifiers. Here we assume some functional forms for probability of x given y, and also the probability of x. And these classifiers aims to estimate parameters of the probability of x given y and probability of x directly from the training data, and then use Bayes' rule to calculate the probability of y given a particular x. So logistic regression is a kind of discriminative classifiers. One important concept in logistic regression is called odds. Odds is defined as a ratio of the probability of a positive outcome to the probability of a negative outcome, because we consider only two classes. So the probability of negative outcome is just 1 minus the probability of a positive outcome. And we know probability have a range from 0 to 1. Therefore, the odds has range from 0 to infinity. And if we take log of the odds, then the range, this is called logit, and the range becomes from negative infinity to positive infinity. So the logit is the log of the ratio of the probabilities over here. So that is how we map a range from 0 to infinity to a full range from negative infinity to positive infinity through the log function, so that we can model it use a linear function. So that maps basically our original probability from 0 to 1 to some kind of output that have the full range, so that we can model it more easily. And now we have the logit function. We use linear regression on the logit function, and this is logistic regression. So basically, this is a logit written as a log of the ratio, and we model it use a linear regression like this. And more generally, we can use also basis functions to model the logit, such as this. And in the following, we will use a simpler form over here. And then this logistic function, or which also called sigmoid, will actually be the inverse of the logit. And if we do some mathematical derivation, we can inverse the function of logit over here to obtain that the probability of positive outcome, which is pi, is actually equal to this form. It is a ratio of 1 plus exponential function of a linear combination of the input. And as an exercise, you should be able to verify the odds by using the equation over here. That is, you compute the ratio of this value over 1 minus this value. Therefore, we can see through this logistic function, we have mapped the logit, which has a range from minus infinity to positive infinity, to a probability with range from 0 to 1. And this is the nice logistic function you have seen in the previous section. So how can we learn the parameters, which is W? And we need to make some simplifying assumptions, which is the common assumption that the data are conditionally independent of each other. And then we can write down, we can simplify the likelihood as the products of the individual, the likelihood of the individual data points. And then we can make use of the Bernoulli distribution for binary classification, where we denote the probability of positive outcome as pi, and the probability of negative outcome as 1 minus pi, and this is often modeled as a coin flipping. And then we can write these two probabilities as a single equation using y as a switch in this form. So you can verify when here, when y equal to 1, this becomes 0, and this becomes 0, this becomes 1, and so p1, y equal to 1 equal to pi. And likewise, when pi equal to 0, we have 1 minus pi. So we write these two equations into a one equation by using y as a switch. And the probability, we can estimate the probability of y equal to 1 for given each data point by computing the frequencies of the positive outcomes. And then we compute the log likelihood, that is the log of the likelihood given the probability of y given x. And based on the independence of the data points, this will be written as a summation of the probability of y given each data point. And then we can simplify it into this form. And The negative of this, the negative log likelihood of this is called cross entropy, one of the most popular loss function in neural networks. And to get the solution, there's no there's no closed form solutions, and therefore we use a maximum likelihood estimation. And to obtain this maximum likelihood estimation, we can use SGD, stochastic gradient descent, on the negative log likelihood. So basically, the negative log likelihood converts the maximization problem to a minimization problem by putting a negative sign on this likelihood. So that is logistic regression. Recall that I have emphasized the issues in machine learning ingredient, and let us look at the ingredients of logistic regression in terms of the data, the model, the evaluation metric, and optimization. For the data, it's more nothing special over here, standard preprocessing, and you need to standardize the data to zero mean and unit variance. And in terms of model, the structure or the architecture is simply a linear relationship between the output and the input, although there's a transformation, but the relationship is linear because we have only linear transformation of the input over here. And in terms of hyperparameter, in the previous presented form, logistic regression actually has no hyperparameters. That is really actually a very good feature because it is very simple to use. But in practice, you can use regularization, and then you will have a regularization parameter as a hyperparameter. You will see this in the lab. And the parameter is basically W, what we are going to estimate. And to estimate that W, we maximize our evaluation metric is the likelihood. Basically, we are going to maximize the likelihood or minimize the negative log likelihood. And the optimization is achieved through SGD or other similar optimization algorithms. And an interesting view of logistic regression is we can view it as the simplest neural network, where the input layer is the data, and we can view this as the output neuron, where the first block over here is simply a linear mapping, which is often called fully connected layer. It's a linear combination of the input into a variable z. And then we pass this variable z to an activation function, which is the sigmoid, and to obtain an output with a range between 0 and 1. And then we can do a thresholding to determine the binary output. And it can appear showing various forms, right? For example, here it shows in a little bit more details. This is a input features, and that is a weight, and through linear combination of the input using the weight, we have a network input function, and then we apply this activation function, the sigmoid, to the transformed, the weighted sum over here. And in the process, we're trying to minimize the negative log likelihood or maximize the likelihood of data. And in decision, we need to do a thresholding, which is called, we can call it unit step function, to obtain a binary output. And this is another commonly used representation where they put the linear mapping summation on the left and put the activation function on the right of a circle represent a neuron. And that is how we can use logistic regression to do binary classification. But how about multi-class classification? A simple way is to do the so-called one versus rest logistic regression. That is to run multiple binary classifications for all possible classes. For each class, you classify between that class and all the remaining class will be considered as another class. And then if there are 10 classes, then we basically do 10 binary classifications. For example, for digits, we classify 1 against 2 to 9, and then we classify 2 against 1 and 3 to 9, and so on. And then we pick the one with the highest value, because logistic regression give you an output in terms of probability. So we can pick the one with the highest value as the class for that data. And we can also do it in a more mathematical way, which is called multinomial logistic regression. And this is also known as softmax. So this approach basically generalizes the logistic regression to multi-classes by generalizing binomial distribution to multinomial distribution. And then that generalizes the sigmoid function to the so-called softmax function. And this gives us a linear classifier for multiple classes. So this finished the introduction of this very important logistic regression. So logistic regression is a discriminative classifier, directly model the likelihood of the probability of the output given the input. It is a simple linear classifier that retains a probabilistic semantics. And the parameters in logistic regression are learned by iterative optimization algorithms such as stochastic gradient descent, because there's no closed form solution. And we can view it as the simplest neural network. So in the next section, we will look at computational graph.